Okay, hello everyone. I guess it's time to start. I'll leave the door open for a while longer in case there's some latecomers. Today I'm going to talk about system testing for scientific software. Well, in particular, one example of how you can do this. This is not the holy grail, but hopefully it can give you some inspiration on how to test, well, system test any kind of software. So I will start with a small introduction. Well, I would if this worked. Sorry about that. Okay. My name is Torkel. I work for Itema in Trondheim, Norway. It's a small consulting firm. We are about 27 engineers and a few other office personnel. All we do is consulting, but we do just about anything from games on iOS to Android apps to Eclipse applications, etc. I've been doing Eclipse for quite a while. I'm a committer at a few projects, and I'm also involved in the science working group, which you might have heard of. For the past few years, I've been working on a project at MARINTEK, the Norwegian Marine Research Institute, where we have been building a marine operations simulation workbench. I will show you a little bit about it later. If you want to reach me, there's some contact info in the bottom there. I will put the slides on the website later. So, anyway, system test. Why should we have those? I guess all of you have unit tests on your applications, obviously. You probably have some integration tests too when you integrate certain modules. But system tests, what's that? Well, it's when you have the whole entire stack of software being tested. You have a vertical slice. You start from the top and you bottom down. And we have a very complex application, so we need to test it in this way. We need to ensure that the system works as it should and not just individual parts. So I will get back to that. I will just introduce a little bit about the team and what we have been doing. The pictures to the right there is from one of the laboratories. It's called the Ocean Basin. It's a swimming pool, basically, 50 times 80 meters. It has seabed. The bottom can be raised, so you can get depths up to 10 meters and nothing. And there are, I don't think you can see that, but there are some fans. We have fans on 3 sides, so we can create winds, strong hurricanes. And there are wave generators on 3 of the sides, so we can create both waves and wind and create, well, so you can see in the bottom picture there, those are quite strong waves for this model of an oil rig. So anyway, we have 3 research scientists that are product owners. These are the guys who knows how to use the application, how to use the, well, they're talking with the customers, they are designing the simulation cases, etc. And we have 6 software developers that are actually developing the workbench based on Eclipse. And we also have 2 research scientists that are doing the physics engines, the one that does the actual simulation. So what we are doing with the Eclipse application is building the interface to the physics engine, because basically that is a number crunching thing where you have a text file with some description, you put it in, crunch numbers, and you get a text file back with the results and read that into the UI, and we can present it in a way that makes much more sense. So this is a typical user story. The research scientists, the product owners will figure out what we need to do. They use Jira, fill it out, something like this, add a few attachments with, for instance, to the right there, the math that we need to do for this particular case. So we have a pretty good description of what we need to do. We probably have some sample input data. We have the math. We have a possibly a description of how it's supposed to be in the user interface. And we basically know exactly what to do. What we don't know is how to use this particular feature when it has been implemented. We have no idea. We are programmers. We just write the code, and we can play around with it a little bit. Because we've been using the application for so long, we know a little bit about how it works, but we are not able to write a decent case for that. So what we do is we typically write the unit tests. Those are obviously quite straightforward because you have boundaries. So you can test for those, and you test each single method. We do the integration tests on the components involved. And here we have two components, which is the hydrodynamics part, which is a core feature in CIMA, the application that we're developing. And there is a part of the new feature that we've been working on. And lastly, the system tests, which we're going to talk about now. So normally when we write the system test, it's done by the developers. It's quite time-consuming because there's a lot of rigging. We are programming the test case, and we are programming the test itself. And we need a bit of knowledge about the domain to be able to do a proper system test, because we don't test the entire application. We just take this slice and we just make sure that what we're testing in this slice makes sense. Because sometimes it's just, if you don't know what you're doing, you're probably making a bad test. And it can be very hard to maintain, because if we do changes to the data model, we also have to do changes in the tests, because the tests produce a set of data depending on the model. So it's quite sensitive to changes. But we've come up with a solution that we think is working nicely for us. We're going to talk a bit about that. Martin Fowler, I think you probably heard about him. He wrote a few white words about DSLs, domain-specific languages. And that's basically what we've been doing. We have implemented a system test DSL, very basic one, but it allows the scientists to write the test themselves. So we have put the entire test framework into the application that we've been developing. So the scientists, they can design their own cases, the simulation cases, and they can script the test. So when they're done with their stuff, we will take this test case, the data model used for the test case, put it in a folder, and it will just be picked up by the nightly build system and executed, and then it's done. It also enables customers to verify that their simulations that they've been running before does the same thing the next version they get. So they simply add a small script that checks certain values, and when they get a new version, they can just run that script and verify whether or not it's the same. We've done this using Xtext, which is probably familiar to many of you, at least you heard of it. We had added a few asserts, simple comparison of values from the data model, or actually the simulation results, and constant. We had added interface to control the simulation, so you can start it and stop it, pick values. We added a way to embed wiki markup, so you can have a description of what's going on inside the script. You have a description and a test and some more description maybe, explaining why you're doing this. output for now is HTML. We're planning to extend this to PDF. So you can, when the test has been executed, we get a PDF that we can just put into the documentation of the product. So when the customer gets it, he knows that those system verification tests has been executed, and the result was so and so. Yes, of course, and the DSL is embedded into the product. We don't send it out to all customers. It's on an update site, so, or a P2 repository. So the scientists would just point to that P2 and install from there. So I'm going to talk a little bit about how we implemented this. We're not going into details, but it's quite straightforward because we didn't really do that much. We just wanted a proof of concept to see if this is something we could continue on. And the conclusion was we should continue. When you set up a new Xtext project, it probably, it does most of the work for you. Everything you see here is generated. And there's a few files that we have modified. It's the grammar file, the Xtext file. This is where we define our language. And we also modified the configuration for the DSL generator. It's a script that is being executed when you modify the grammar and you want it to generate the code for your DSL, the editors, and all those bits. And also the output generator, which is describing what happens when you're running the script, when you're running your DSL. And it can do a number of things. You can produce a file. It can pop up a dialog and say something on the screen, or whatever you put into there. We are using this to execute the simulations and to obtain data and output those data into HTML files. I'm going to show the grammar. Well, part of it's extremely simple. This is basic comparison, and we have, I will show the post processor, but we have what we call a slot, which is a box where the signal comes out and goes in. So the slots are connected, and we're just saying, okay, have this slot. What is the value of this signal in that slot? And you have a number of boxes with different values. I think we will show that in the demo. We were still working on the grammar. This is kind of what we have working now. You can see here that there's a section called markup, and you have a language. It's textile, Markdown, Confluence, and we're using Mylin docs and the parser there to convert the markup into HTML. So whatever is supported by Mylin docs can easily be added here. I think we're going for common mark these days, Markdown or common mark. Yes, and we wanted to include content assist for the wiki grammar, but that proved to be difficult because Xtext doesn't support lexer multiplexing, so we cannot have switch between different languages. We have to put everything in the same. So that turned out to be difficult, but we are talking with the Xtext guys, and we can get some help finding a different solution. That's pretty much the only file I modified for the UI. That's the content assist processor. So you press Control space, you want something to happen, you want a list of something. And this one detects when you're in a certain position in the script. So if you have a slot named something, you press Control space, you should get a list of all the slots that matches whatever prefix you put in there. So just as content assist usually works. So it was quite straightforward. So why did we choose Xtext? Well, it's proven Eclipse technology. It's been around for quite a while. It has great support in the community. Creates results very fast. We didn't spend much time, just a couple of days of getting this rudimentary part to work. so we could understand that this is something we wanted to work more on. And it generates everything you need for the IDE, the user interface. So you get content assist, you get outline view, you get the hierarchy in the navigator. So if you see, well, that's part of the outline too. But all those bits are generated automatically, so it's quite straightforward. We did think about a few alternatives. For instance, ease. I think we could use that to run the scripts and produce what we wanted, but at the time it wasn't really, we didn't feel it was ready. And we wanted to produce a DSL that is closer to what the scientists use. We don't want them to learn Python, although they probably know that already, but certainly not JavaScript. We felt that it was better that we created a language that is more suitable for them. You could also use Antler. I don't know if you're familiar with Antler. You basically write everything yourself. It's a lot of fun, but it takes much more time, and you lose the automated stuff or the generated stuff for Eclipse, so you need to do that too yourself. It's plenty work. So I think I'm ready for a demo. This is the case. Actually, this is an example of the case that I'm showing. This is a semi-sub. It's a semi-submersible oil rig. So it's a lot taller than you can see on the picture, but they fill ballast water in the tanks, so it's kind of floating quite heavily in the water. And these are anchored chains. And what you typically want to do is to check that those are not stretched too far, so they will break. And if you have a storm, there is a lot of stress on those, and suddenly they can just break. And if a few of them breaks, then the platform can just turn around, and you have an accident, which you don't want. One of those, I think, yeah, this one was costing $350 million in 2009. It was a used one, so they got it cheap. We'll try for the demo. Just give me a second. So, okay. Yep. No, shit. Sorry. Something bad happened here. Okay. I'm running this on Windows because I don't have the physics engines compiled for Mac, but everything else works on Mac and Linux. So, okay, so what you're seeing here is a basic Workbench with a few examples included. Here's the semi-sub. Let's open the 3D view so you get an impression of how it looks like in the simulation. Okay, so this is very similar to what you were seeing in the picture. And you can see these parts here. Those are anchors, and these are pipelines where the oil is coming from, or gas, could be gas. And this is how it looks like when it's modeled, and I already ran the simulation, so this is the dynamic mode. Let's see if I can try to find a nice angle. Sorry. And let's see. Something like this. Okay, so I'm just going to run the simulation now to give you some impression of what it looks like. So you see the waves moving, the platform is moving, and while all of this is happening, there's a pull on those chains. They would change color. Well, you can see this one is red, which means bad, basically. So there's too much stress on this one, and that is one of the risers. So, well, it looks like this. The presentation is not that interesting in itself, but it can give you some impression. So when you're running one of those, you can take just a visual inspection, and you can quickly see whether or not this is okay, because, well, in this case, the platform is moving quite a lot. So maybe you put some wrong values into there. Maybe the waves are way off or something like that. So here is, well, this is how the workbench looks like, basically. So we have the semi-sub here, which is called a floating body. The graphics that you were seeing, the drawing of the platform, that is mostly for illustration, because we don't really simulate those bits. It's just a number of points and connections between them, springs and struts. It does have a mass. There's a geometry file, which is the drawing. The catenary system, which is mooring lines and the risers. We have different line types, so you can define what kind of materials you're using, etc. Various kinetics, forces for the various waves, how they're behaving, etc. So there is a lot of parameters gone into this. And this is a typical case that you want to verify works the way it should. So we have this simulation being executed. We have what we call a workflow, which is using the semi-sub case. It runs it through this post-processor, and we have a result. And the post-processor is taking one run of the simulation, collects the peaks, finds the distribution, also runs this through the low-pass filter, and we have a result. So we have various editors here for choosing or setting up parameters for the various filters. So what we typically do is that you have a post-processor, you have a workflow, and in the workflow you put a range of values that you will iterate over and run it through the workflow, and you have a result. So let's look at the test script. After the simulation has finished. So I'm just checking the time here because that clock there is wrong. So I don't spend too much. Okay. This is the test script, which I'm trying to open now. It's very simple. This part generates build info, so we take information about which build this was, who built it, what build server, etc., and we can put that into it, so we have that information. This indicates that the following section is Markdown. Run this workflow, collect the results, and we have the various asserts here. So results, signal, and there's a long string. As means presented as. Don't write this terribly long string, but show it in the table as this. and it has to have this value. And the standard deviation, that can vary a little bit depending on the numerical issues with physics engines, but usually this is quite okay. So we only test a very narrow piece of the simulation, but if something is wrong here, then we know we need to dig into things. I can try to show you, let's see. So I think you will find that, yes. So this corresponds to a box. So example semi-sub, max, is this one here. So it passes through that box. And here you have the signal itself, one of the waves. So the total wave elevation from this, you can look at this. Let's see. Oh, there was nothing there. Oh, I have to run it without the workflow. Anyway, let's go back to the test script. And when I run this, it starts the simulation again. Didn't have to because I already did that. And it will collect the results, compare them, and put it into an HTML file, hopefully. Okay. Yeah, while we're waiting for this, any questions?
So the test scripts were kind of replacing the GUIs. This is like a automating the GUI and the dry sets of the simulation, so basically.
So they use this GUI to model the case, and they will do often they will do the calculations by hand. So they know that the wave cannot, or the chain cannot be stretched, but the forces on the chain cannot be more than a certain value, and they will write this script to validate that. It's very hard to set up these cases because you really need to know your hydrodynamics, and as a software developer, we usually don't. Yeah, I don't know what's going on here. It just takes too long. It is working though, but. So I can show you, let's see, I can show you how content assist is working. If you can get,
You don't specify any tolerances in your assertions?
No, it's automatically detected by the precision you specify in the value, the constant. Yeah. Yeah, so it's let's see, there you go. I have to admit I don't know what's going on here now. Okay, thank you. I should have used the older version, but that's okay. What we get from using the Xtext tool is that I can do something like this and get the content assist. So if I choose run now and content assist again, then it will propose the workflow task that I have. So you're saving a lot of times because otherwise you would have to look up those values in the diagram, and it's just painful. And in particular when it comes to these signals here which only have names. And the thing is that those can change theoretically each time you run the simulation. So we're using strings. There's no other way, as so far anyway. Yes, I cannot show you more of the demo, I think. I will just close that. See. Okay. Yeah. So our conclusion is that this can be a powerful tool. Xtext is very easy to get started on. You'd need to dig into it a bit, use some time to figure out how to use Xtext because it's kind of weird. And also it uses a language called Extend, which is a derivative of Java, a little bit different. And it does a few things that are quite useful when it comes to generating output from the test running. So if you're generating, like us, a HTML file, it's very useful. We found that our DSL is useful. We haven't integrated it into the nightly builds yet, but the research scientists have their bunch of scripts that they have sitting in their workspaces. So whenever we make a new version, they will run those tests manually, and they will see whether or not things broke. And sometimes they do, so yeah. Yes, we are working on a way of defining the post processor too, because that's, you saw those boxes, those diagrams, and there can be a bit time consuming to set up. So we would like to script that part too. So you can just say that I want a high pass filter there with the frequency of something, and then you go on and just connect those filters using a script. Would be probably much faster than clicking with the mouse. And yeah, we want to produce an PDF for including into the product build. So the tests are executed when we build the product, and we can see whether or not the tests pass without actually having to dig into the build system to see the results. So it should be pretty straightforward. Are there any questions?
Maybe a bit philosophical question, but we used similar DSL for testing, but based on Ruby. We didn't invent the Xtext thing. We just gave them the Ruby APIs, and
Yeah.
they were using, and because we had to set up the data, everything inside.
Exactly.
And you're doing a very simple thing. You're just coding the asserts, basically.
Yeah.
That's the very last.
Yeah. And we leave the rest of the work to the other guys.
You already want to do this with this post processor included, and then you will maybe want to include also set up the data in the same script and so on, and then it will become basically just
the script.
Blown programming language. Why not start from something like that from the beginning?
We wanted to try whether or not this was something we should do. And we already see that, yes, we should do it, and we should add more. So that's what it is. I just spent 3-4 days on investigating it, and I spent a couple of more days when we found out that this was something we wanted to do. So yeah, I agree with, we could have just started and did the whole thing from the beginning, but we wanted to make sure, because we are financed by our customers, and we need them to understand that this is a good thing. So yeah. More questions?
I'm just wondering how this fits with things like Squish and Drupal. It's a similar question to what you asked. But, we use Squish, so we will bring up the GUI, set up the model graphically, and then run the simulation, and then see what the user's been given back graphically. And that's all in Python. But obviously, you don't need all the GUI set up. You're just running the
One aspect of it is that we want the customers also to be able to use this script. So those who buy this application, they will have their test cases. Typically they own a couple of oil rigs or ships or whatever, and they model this body in a particular location with certain weather data, and it's a case that doesn't change a lot. So you know, it's static. If they change the anchor chains, they will update the information on the model, and they can run simulations again. So they will end up with a library of models that they use. So there is no need of generating a lot of models, because they have those a dozen. So the thing they need to do is to define the test case and to run those whenever they get a new version of the software. So basically, that's the idea. It's acceptance testing and system testing in same. Okay. Last slide. Like this. Remember to vote. I know the internet or the network is difficult to get into, but for the sake of everyone who has presented for you today, please go into the webpage and vote when you get back to the hotel or when you're back home. Thank you very much.